exposed to something called the fundamental theorem of calculus. Does that sound familiar?
It's not new.
What's that?
It's not new.
It's not new. Okay, yeah, you should have seen this in Calc 1. Okay, so it looks something like this. And much of this course, Calc 2, is about integrals. So here's a hopefully easy question. Which side of this equation is an integral? The left or the right? Okay, so you should all recognize this as what's called the integral symbol. So this thing is called an integral symbol. Okay, and so Calc 2, a majority of the course has to do with integrals. Okay, a majority of the course has to do with integrals. And that being said, we'd better know what this statement is about. We better know exactly what's going on here in this statement. It's not just a formula for doing some exercises. Okay, it's the fundamental theorem of calculus. Does this sound important? Yeah, right. So this is the fundamental theorem of calculus. So we should know not just how to use this to get answers, but much more importantly, what's going on here. What does it mean? Okay. So we want to take a day or two to kind of review what is this about? What does it mean? And then maybe for some of you, or many of you, this may be new, that it just was introduced to you as a means of doing certain types of exercises to get certain answers. Okay, but that's not what it is, right? Again, this is the fundamental theorem of calculus. It has great, rich meaning, and we should know what that meaning is. Especially now that we're going to apply it throughout this course. Okay? So we're going to spend a day, like I said, making sense of this. What is going on here? All right, what is going on here? So the first principle about this is rate of change. Okay? Rate of change is a huge player in this thing here. Okay, so let's look at a really easy example. So you're buying trail mix that costs $3.20 per pound. Okay, and that's an example of a rate of change, okay? An easy rate of change, right? So after scooping some of the mix into your bag, you decide you want more. What additional cost will you pay for 1.5 more pounds of trail mix? Okay, so I want everyone by yourself to answer this question. And you should be able to answer this without calculus, right? This is very fundamental. You should be able to answer this without pre-calculus. But there's a principle here that's crucially important, okay? So everyone, I want you to figure out how much additional cost will you pay for 1.5 more pounds of trail mix. Everyone do it. Everyone do it. Okay, so in the light blue shirt, over there, in the first row. Yeah, you.
You just multiply 3.2 by 1.5.
Okay, why?
Because it's basically 1 pound is $3.20.
Okay.
And then half a pound is half of that.
Right.
And you add it to that.
Okay, so he said you're going to take the 320. If every pound is 320, you're going to take the 320. And you're going to multiply it by 1.5 because for every 1 pound is 320, so 1.5 pounds will be 1.5 times 320. And what'd you guys get?
40.
Okay, so this is the basic idea of rate of change. That if you want a total amount of something, you're going to take the rate of change by, in this case it's per pound, so by the number of pounds, or times the number of pounds, and that will give you the total amount of cost. Okay, but so this thing has all these variables, letters in it. So we want to kind of start bridging the gap between this principle and all these letters and symbols. So I'm gonna give you a set of variables below that match up with this situation. You're gonna define the variables. Okay, so we're gonna use letter K to mean the rate of change. Okay, and so I want you to, given this situation, I want you to define all these variables. What is the meaning of x, y, delta y, and k? All right, and then I want you to meet someone next to you and at least check your work with them. If not, you can work together, but at least check your work when you're done. So can you be specific? What number of pounds?
Number of pounds in the bag.
Number of pounds in the bag. What do you guys think?
Number of pounds of trail mix.
Okay. Yeah. So so total number of pounds of mix in the bag. Right. So yeah. So total number of pounds of mix in the bag. And so then what about y? Patrick.
It's the cost for that pounds in the bag.
The cost for that amount of pounds in the bag. What do you think? Agree?
Mm-hmm.
Yeah. The cost of X pounds of mix in dollars. Okay, so what is this? So hopefully we're also familiar from Calc 1 with this. Delta X. Delta X. What is that? Tyler, do you know?
It's a change in quantity of trail.
What is it?
The change in the amount of trail mix in the bag.
The change in the number of pounds, right? The change of the number of pounds in the bag. Okay, so let's go through it. In the situation that I gave, what's known and what's unknown? Is X known? Is that a known quantity in this situation?
Yes.
So lots of yeses and one no. Tell me why. Why not?
Well, it doesn't tell you how much trail mix you start with.
Yeah. Was it only tells you?
It only tells you how much you added.
Yeah, it only tells you how much you added. So what is that? What's the 1.5 more pounds?
Delta X.
A delta X? Yeah, that's the additional. It's a change in number of pounds. So this is saying this is like a change in what? The total number of pounds in the bag, which we don't know. But we know what the change is. All right, what about Y? Do we know what Y is?
Yes.
Corresponding change in cost.
It's 4.8.
Y. Is it change in cost?
No, it's how much it costs.
Do we know what that is in this situation?
Yeah. It's K delta X.
It's the same as delta X.
No, it's K delta X.
Okay.
It's-
Do we know the cost of all the pounds of trail mix in the bag?
No.
No, we can't. If we don't know what X is, we don't know what the total number of pounds in the bag is, because so we can't know the total cost. Okay. Okay. Now what is delta Y?
Change.
Isn't that what we're talking
No, I pointed at the screen 3 times. I was talking about Y. I was talking about Y.
about? Okay, no.
Okay. So what is delta Y? What is
K
delta
delta
Y?
X.
We're defining it. What is delta Y? How is delta Y defined? How is delta Y defined?
What we define it as?
Yeah, the way we're defining these other things.
The change in cost of mix in the bag.
The change of the costs, right? The change of the cost in dollars. Okay? And what about, and do we know what that is?
Mhm.
How do we know what that is?
Because we know the change in the amount of trail mix we have, we know the rate at which it is, so we do know the change in the total.
Okay, so we'll talk about, that's key, and that's the answer to our question, right? What additional cost will you pay? That's the answer to the question that I asked. All right, and K is?
The rate of change.
Yeah, yep, the rate of change, which is 320. Changed the problem, but didn't change that. Okay? Dollars per pound. Okay, so now I'm to write an expression using one or more of these variables that computes the answer to the question above. And the answer to the question above was, what additional cost will you pay? So which variable was that again? The additional cost you'll pay? Which variable was that? Delta y. So write an expression using those variables, one or two or more of those, that computes what delta y is. And we simply said that 480 was, oh, well, you're just going to take how much you pay per pound and do what? And multiply it by how many pounds? So what is this expression? What will it be? Right here? Yeah. No, right here. Yeah. Yes.
In variables?
In variables.
Delta y equals k multiplied.
How'd she do?
Great.
Okay, so this is the symbolic version of this very important principle. Okay? And you all should have been able to do that when you first asked the question. So mathematically, you got these numbers, you can make out the answer. But so now symbolically, we have this version of that. That your change in your kind of your output quantity is your rate of change times your change in your input quantity. So if you're going 65 miles per hour for 2.3 hours, how far do you go? So another example here. So I want you to find the answer and relate it to this. Talk with the person next to you. Find the answer to that question and relate it to this principle, this expression right here.
Yeah.
Okay, so back here, glasses and pretty necklace. Tap on her shoulder. So, what's your name back here? Yeah.
Oh, sorry,
What's
Gina.
What is it?
Gina?
Gina. Can you, so, if you travel for 65 miles per hour for 2.3 hours, how far do you go? And then, how does that question relate to what we just wrote down here?
You said 65 times 2.3 because you do delta y as a change in distance, k is the 65 miles per hour, delta x is a change in height.
Okay, and what did you get for an answer?
129.
When was it? 129.5?
49.
149.5. So you go 149.5 additional miles, traveling at 60 miles per hour for 2.3 hours. That's the additional amount of time that you've done. Okay? So, easy idea, certainly easy question, easy idea, but really important that you relate it to this little statement right there, delta y equals k delta x. Okay, so let's keep going here with this. So now we're back to the trail mix, and we're going to remove 0.4 pounds and return it to the bin. Okay, when no one's looking. Okay, so I want you to define delta x, delta y, and k, and make a appropriate conclusion. Okay, so define delta x, delta y, and k. So negative what?
And so the result is
Oh, what is delta x?
negative 0.4 pounds. Pounds trail.
Yeah, assuming that our definition of delta x is the same, right? Our definition of delta x is still the same. That it's the change in the pounds in the bag. Okay? And what is k? Is k negative 3.2?
K is the same.
K is the same. Agree? Yeah, the rate of change is still positive. If you buy more trail mix, your cost is going to go up. So it's still this positive value, 3.2. What are the units on that?
Dollars per pound.
Dollars per pound. Okay, and so then what does that make delta y?
Delta y is negative $1.28.
How did you get that?
What I did is delta y equals k times delta x.
Okay,
And so the result is either negative $1.28 more dollars or $1.28 fewer dollars.
yeah. So if we just go strictly by the numbers that we have so far, we get negative 1.28.
Yeah, dollars.
And so what does this mean in negative? Somebody knew. What does this mean in negative? Good job, by the way. So what does this mean negative dollars? What's your name?
Brandon.
Brandon.
So it should mean that there is a loss of $1.28 in value.
Okay. So it means that what you're going to pay, just what happened to what you're going to pay for this bag of trail mix?
Save.
Decreased, right? So you save that much, or it went down that much, the total amount you're going to pay went down. Okay, so negative, this is an important idea, and when it changes and rate of change. With changes, if you have a negative change, that means it's a decrease. Okay? So if we have a decrease in the pounds, our negative delta x results in a decrease in the price. Negative delta y. Okay, new situation. A soldier lowers an American flag from the top of the pole at 0.75 meters per second. How much does the height change from 0.6 seconds to 2.4 seconds since the flag left the top of the pole? I don't want you to do that. We're going to do variables first, okay? So I'm going to give you one though. I'm going to tell you that y is defined as the height of the flag above the ground, okay, in meters. All right, so there's some subtleties here. You got to think. Make sure you get all the details, okay? So y is the height of the flag in meters. So I'm going to give you that one, and I'm going to leave it up to you to figure out the rest. And then whatever is known or unknown. So after you get the variables defined like this, like in words, as phrases, then you're ready to start applying numbers. Time the flag's been lowering. Okay. So this was the way I phrased it, the number of seconds since the flag left the top. Okay? Number of seconds since the flag left the top, which is the same as what he said, total time the flag's been lowering. But you want to have seconds in there.
All right.
Yeah, when you're defining a variable, make sure you give a unit. Okay, and y we already said was the height of the flag in meters. Okay, so delta x. So are either of these known in this situation? Do we know the number of seconds since the flag left the top or the height of the flag in meters?
No.
So far, 2.4.
Yeah, we have two different x values, right? We have so this 0.6 seconds, that is a particular value of x. And then sometime later, we have another value of x, 2.4 seconds. So we have two different values of x. Do we have any values of y? No, we don't know how tall the pole is, right? We don't know where it starts, so we can't know any values of the height. All right, what is delta x? Can you tell me what delta x is?
The change in the time to lower the flag.
The change in time spent lowering the flag, right? The change in time in seconds, that's right. All right, and then delta y?
The change in the flag's position on the flagpole.
What kind of position?
Is meters from the top to the bottom, or wherever it's going to.
Yeah, change in height, yep. Change in the flag's height in meters, yep. Okay, and what is k? What is the meaning of k? Right here.
The rate of change
Okay,
of the flag so as it goes from the top to the bottom.
okay, the rate of change of the flag as it's moving, and what is the value of k?
Is that 0.75 meters per second?
Okay, 0.75 meters per second. What do you think?
Negative.
I'd like to call it negative.
Should be, so simply we're saying negative. Should be negative or positive.
Negative because of low.
If the change in time increases, what happens to the height? It's going to decrease, which means we need a negative rate of change. That was the difference that I was hoping you catch, and some of you did. Okay. So k is the rate of change here, but since y is defined as height, this positive value, and that positive value is decreasing, then that rate of change as a numerical value is negative 0.75. Okay, so now I want you to apply the variables to this question and solve the question if you haven't already. Okay, so now we're going to apply. So what is what in here in this question, and then answer the question. Okay. So write an expression using these variables that computes the answer to the question below.
You want to use a less efficient.
Okay, so what's the expression using these variables that computes the answer right here? You don't know? Okay. Which one of these is do you know which one of these the question is asking for? Which one of these is the question asking for us to solve for?
Delta y.
Delta y. Okay, and so how are we what's a way we're gonna solve for delta y here? You know? No? Brock?
You gotta find x. Well, I found x first. The total number of seconds flag being lowered and then multiply by the rate of change.
Okay, and so the expression will be?
2.4 minus 0.6 is 1.8 seconds. The flag being lowered.
Okay, 2.4. And how do we use symbols for that? What symbols for that?
X.
Is it x?
Final minus x initial.
Right, and that's computing what?
Negative your actual x, the number of seconds the flag's being lowered.
Is it x?
Delta x.
Delta x. Okay, and then you said that, what is that, 1.8?
1.8.
Okay, and what else?
And then multiply that by the rate of change, which is negative 0.75.
So you're going to multiply these together.
And got negative 1.35 meters.
So it sounds like you're doing k delta x. Is that right?
Yes.
And you got what?
Negative 1.35.
Meters?
Yes.
So it's below the ground then. Flag is below the ground 1.35 meters because it's negative.
No, it was lowered below the top.
Yeah, is this y? Is this y do we know?
It's changing height.
Delta y, right? Delta y. And so this makes sense. As time goes by, the change in height should be, the change is negative, meaning you have a lesser height now. It's a decreasing height. So that amount of change was negative. Yeah, so just emphasizing here that we're not dealing with values of x and y, right? We're not dealing with values of x and y. We're dealing with values of delta x and delta y, right? Change in time and a change in height. That's why it's perfectly legitimate for this to be negative 1.35 meters, because that's not the height, that's the change in height for this change in time. Okay, does it make sense? Anybody have a question? Okay, so don't answer this yet, but you can think, so what does this have to do with that up there? Don't say anything, just, can you make some kind of connection to what it has to do with this thing called the fundamental theorem of calculus? Some of you might have an idea, some of you may not. Okay, so let's look at this. So we're looking at this got a graph over here. All right. Can you make sense of this graph with the last example that we did? So look at the last. So look, thinking about the last example we did with the soldier. Can you make sense of that graph? And so, what does that mean? Making sense of that graph. What is this? Okay, everyone, think about it and then talk. Not. It's okay. So, what would this axis represent? What quantity and what unit? What would this axis represent? What quantity and what unit? So think about it and talk amongst yourselves. So delta y. And so what does that represent and what's the units of that? Negative 1 point something? What do you think? Go ahead.
The height in meters with respect to time.
The height in meters with respect to time. Okay. Is that delta y?
I think so.
Okay, so delta y, and it's the height in meters with respect to time. Okay? Agree? Some nods? No, disagree.
Okay, K is, the rate of change, which is the height with respect to time.
Okay, the rate of change.
Yeah, that's what I just in meters.
So what is delta y? What does delta y represent?
K delta x.
No. What is the meaning of delta y?
Change in height.
The change in height. Is this graph showing the change in height?
No.
Yeah, it's not showing delta y. It's not showing delta y. What is it showing?
It's the rate of change.
It's showing the rate of change, which is? It's k. This graph is k, right? What is the value of k? Right, and so what is this graph telling us about the rate of change? What is this graph showing us about the rate of change? That it's constant. Is delta y, is the change in height constant?
No.
I mean, I don't even know how to really answer that, but like in terms of how to graph that, I guess if you were graphing it, no, right? So no, delta the height is not constant, and so delta y is not constant. But what is constant here? This value negative 0.75 is the rate of change, and so what are the units for that?
Meters per second.
She wants meters per second. Agree with that?
Yes.
Meters per second. Let's start over here. So yeah, so this is meters per second, and this is our value of k. Negative 0.75. Okay, what about somebody here? What about the x-axis? What about the x-axis?
Would it be seconds?
You want seconds. So what variable was that we were using? Delta x? Is this delta x?
It's just that.
Just x, right? This is just the time spent lowering, right? The time spent lowering the flag, or the time since the flag left the top of the pole. Okay, so we have a graph of given how much time has gone by since we started lowering the graph. This tells us what? This graph tells us. So like if I come right here and I pick a point right here, what does that point mean? What does that point? Did I add a point to the graph? Did I just add a point to the graph? What did I do?
It's already there, you just signified it.
Yeah, I highlighted it, I signified it, right? So we're going to highlight this point right here at x equals 2.1. Say, what does that point mean? What does it mean in the graph? Yeah.
At 2.1 seconds, the rate of change is negative 0.75.
Well said, right? So it's at that point represents two quantities together, taken together. At 2.1 seconds, the rate of change is negative 0.75 meters per second. Okay, and so then what's the rate of change at 1 second? Negative 0.75, right? So this is showing us the constant rate of change, that it doesn't change no matter how much time has gone by. Okay, so now let's think about this. So we're lowering a flag, and this soldier is lowering a flag. We don't have a machine doing it, the soldier is lowering a flag. How about this rate of change function? Like it?
Don't we have to put some constraints on it?
What do you mean?
What happens if we lower the flag to 0? I mean, at 0, the rate of change is, I guess, ostensibly still constant, but we
Yes.
can't lower it anymore.
Alright, so so we would want to say that it takes whatever 12 seconds or 18 seconds, and then we would stop.
Yeah.
Okay? Fair enough. So I'm only showing the first 3.5 seconds. So what about for these 3.5 seconds? Like this rate of change function? Reasonable?
It's reasonable because it's constant. The rate of change is constant.
Everyone agree?
We could,
Well, that's what I told you, but now I'm asking you to think more about the situation.
I don't like it because if it's a soldier, then why is it constant? What if there's variation?
Because we're perfect.
Obviously.
Okay, so I have an alternative. So I want you to make sense of this. So I want you to look at this, think about this, and talk about this. Make sense of this as also as a rate of change function. Okay, rate of change function. Okay, go. All right, be specific, okay? So I want you to think through it specifically. So it's still rate of change. This is still seconds. So think, because
He's not going on it, he's between hands.
He's
changing hands, right? It's changing hands, right? Changing hands. He's gonna pull, and then when it's changing hands, for a moment, the flag's gonna do what?
Stay still.
Stay still. No, it's not gonna move. And then he's gonna pull the other hand. And then it's gonna stay still, and then he's gonna cross over and pull the other hand. So this is changing hands, right? Changing hands. Okay, so what did we calculate for how much the flag went down between, what was the question? 0.6 and 2.4, and we calculated that to be?
Negative 1.25.
So our delta x was what?
Delta X is 1.8.
Before? Our delta x was?
1.8 seconds.
1.8. And what did we get for the change in height?
1.35.
Negative 1.
Okay, delta x. Actually, if the soldier's doing it according to this rate of change graph, he is perfect.
Because it's
He
periodic.
is perfect because he's doing it perfectly. You know? Alright, so we had k was negative 0.75. And we got negative 1.35 feet. Meaning the flag went down 1.35 feet in those.
Meters.
Is it all meters? Thanks. Meters. So now, the more realistic situation, we're going to look at the same change in time from 0.6 to 2.4. Does the flag also go down 1.35 meters? Or does it go down more, or does it go down less? Given this new rate of change function that I'm giving you.
Less. Is it more stuff?
Some people are saying it's going to go down less, according to the new rate of change function. So the same, more, or less? What do you think? Less? Why less?
Because of the rate of change decreases.
There's some places in here in this time frame where the rate of change is less, right? And so that's going to, when it's not, it's constant, negative 0.75 anymore. So because we have these areas where the rate of change is less, then the total amount that it's going to go down is going to be less. Agree? Okay, so how much? What's the rate of change, or what's the total change in the height of the flag?
It's not
All those rates of change added together.
All those rates of change added together.
I know what I'm trying to say.
Okay.
That's what we're
Yeah. Okay. So you got an idea there. That's right. We're not adding rates of change. So easy or hard question to answer?
You need to give us an expression for that periodic function.
What's that? Okay. Even if I did, well, so you want to see it? You got
Something, huh?
there. It is.
Yeah.
0.75 sine of 4x quantity to the 16th.
It's still very difficult.
Okay, yeah. So what made it so easy to calculate the change in height over here? Why was it so easy? Constant rate of change. Boom, easy. Take the constant rate of change, time for change in time, cranks out the change in height. So suddenly, if we've got this what? Now that our rate of change is changing, whole new ballgame. So this rate of change is changing. How do we get the change in height? Because for lots of time in here, every moment it's changing. Okay, so we need a strategy to do this. So what can we do? We would love to be able to use this principle over here, the constant rate of change principle, because the math is easy. So how can we apply that constant rate of change principle to this? We can't do it for 1.8 seconds because the rate's changing all through that time.
all of the k delta x's added together.
Okay, so we have to define what you mean by that. All of what? We only have one delta x at the moment.
every point in time in that 1.8 seconds.
Okay, so why don't you get started on that and let us know when you're done.
That's what the interval for is.
Yeah, exactly. Yes.
If you give us that expression again, can't we find the antiderivative? Basically, we have a complicated.
Okay, but so why does that work? That's what we're getting at. So yeah, that's where we're going. But where does that come from? Where does that principle come from? Okay, so what we can do is we can apply this thing right here. If we just looked at, say, let's look at intervals of 0.3 seconds at a time. So 0.6, 0.9, 1.2, 1.5, 1.8, 2.1, 2.4. So now let's make delta x, let's cut this thing up and make delta x 0.3. And so looking at this first interval of 0.3, what is k? Yeah, so if you look, it's that whole time, it's negative 0.75. So for the first 0.3 seconds, we can use this, right? We can use this. What about for the next 0.3 seconds? From 0.8 to 0.9 to 1.2. Is the rate of change constant?
Rate of change is
No. It's changing.
It's increasing.
It's increasing. It's right. It's getting less negative. That rate of change is getting less negative. But if we wanted to use that principle over there, k delta x, then what would we need? We need a constant rate. So what if we just kind of slap a constant rate on there that tries to be the changing rate, or is something like on the overall is the average rate. So would I put negative 0.75 for this? Would I put 0? Is that a good estimate for the rate through there? Not really, right? So what would be a good estimate for the rate of change through there?
X cubed?
I'm asking for a rate of change, right? I'm asking for a rate of change that would do a good job of trying, maybe pretending to be what this is.
Negative 0.375.
Okay, so he's saying halfway between. Okay, so what about just negative 0.4? Can we just use negative 0.4?
Sounds good.
Yeah. So what if we just pretended, that's supposed to be straight.
0.3 interval.
So what if we just pretended that it was 0.4? That's better. And just, we'll pretend that it's constant at 0.4 as a way of kind of estimating, maybe kind of on the average, what the rate of change was on that interval of 0.3. Is it fair? So we're going to say that for the next 0.3 seconds, say it's constant at negative 0.4. And then what about the next 0.3 seconds?
Let's do the same.
Yeah, same thing, right? So it's doing the same thing but going down now. So maybe just do it again. And then what about the next 0.3 seconds?
It'll repeat.
0.75. Down there, like that. So this was also negative 0.4. And this is negative 0.75. All right, what about the next 0.3 seconds? Negative 0.4 again? Is that a good estimate? So what about the next 0.3?
Negative 0.4.
Negative 0.4 again?
Yeah.
I think maybe even less here, because so we use negative 0.4 to be kind of, in this 0.3, it's
We have less trouble.
overall it's closer to the x-axis. Do you see that?
Yeah.
So maybe let's go split in half again. Let's do negative 0.2 for that. And then what about the last 0.3?
Why is it negative 0.2 again?
Yep, negative 0.75 again. There's no right or wrong answers for these. I'm just coming up with a constant rate that's kind of pretending to be what the rate is over that interval. Do you see? So you could use negative 0.38. You could use negative 0.41. No. Anything kind of in the middle here. I'm just noticing here in this one, it's kind of, in this interval, it's more of it is closer to the x-axis than in these intervals. So I just chose something less, or less negative, negative 0.2. You could use negative 0.3.
What do you mean more of it is closer to the x-axis?
What's that?
What do you mean more of it? More what?
Because I'm looking at the graph here. So for this, right, like that, that's the part of the graph, and I said I'm gonna guess that's all equivalent to a constant rate of 0.4. But now for this one, it's like this. So do you see that overall this is a more negative than what this would be?
Oh, yes.
Do you see that? So I'm picking something less negative for this one. Okay, so now we can get an estimate, and you're telling me that you think that the actual change in height for this rate.
Oh, no, it's negative 0.4.
My math is probably wrong.
I just took 0.3 times the rate of change in each and added them all together.
Oh, I see.
Yeah, so you simplify it, it's 0.3 times parentheses plus plus plus
Each
plus.
rate of change times 0.3. Each rate of change times 0.3. So, first that's R is negative
This is the strategy that I think most of you. Now we're going to add up a bunch of little changes based on our pretend rate of change function. How many are we going to add together?
6 total.
You want 6. Okay, so the first one, a little bit of change in the first 0.3 seconds is?
negative 0.
That's 0.3.
Okay, and the second one?
Negative 0.4.
And so we'll trust that we got the pattern down. And the last one will be?
Negative 0.3 times negative 0.2.
No, don't do that because that doesn't reflect what we're doing.
Oh, I'm sorry.
Yeah, I mean, yeah, it's the same. You get the same result and maybe faster. But the idea here is that for every interval, we're going to get that little bit of change, and then we're going to add up all the little changes.
Isn't it negative the last one?
Yeah,
Oh, yeah, I forgot the terms.
it should all be negative. Okay, and then so did you get something
Yeah. I
less negative than that? You should have.
Negative 0.975.
975?
Yes.
Cool. And the units on that is?
Meters.
Meters.
Okay, so many things in the world are more realistically modeled with a changing rate of change. There are some things in the world that are constant rate of change, but most things, when you're looking at rate of change, have a changing rate of change. Especially when you're talking about velocity, acceleration. You don't. If you went from 0 miles per hour to 5 miles per hour instantaneously, you would die. Okay? You would, because that's an infinite acceleration, which means an infinite force on your body. Okay? So changing speeds always means changing speeds gradually. Even if it's a quick change, it's still a continuous change from one speed to the other. You don't have instantaneous changes in speed, and so therefore you have a changing rate of change. Changing rate of change. Okay? And so that being said, we want to be able to answer these questions like this one of how much did the flag get lowered in this period of time? And so this is the first step in answering that question is make a pretend rate of change function with constant rates, so we can use the easy math of this, k delta x. And then we can just add them all up. Alright? So hopefully this is fairly accurate. But it's not exact, right? Because it's based on this number is based on the pretend rate of change function with the constant rates rather than the true changing rate of change function for revenue. Okay, so the homework is, I got a handout for you.